After studying this module, you shall be able to learn about an important implication of the Solo model, that is about consumption, optimal savings rate or golden rule savings ratio in the long run steady state. Learn about the basic principles underlying endogenous growth models, understand the role of human capital in the economic growth process, appreciate the importance of saving and capital accumulation for technological progress and economic growth in the long run. Understand the differences between the neoclassical, which is the solo growth model, and the new endogenous growth models. Know about the implications of the endogenous growth framework. In this module, first we shall discuss an important implication of the Solo model regarding the optimum level of consumption and savings in the long run steady state equilibrium. Thereafter, we shall try to give an idea regarding the factors affecting technological progress in an economy and discuss the basic structure, assumptions and implications of the endogenous growth models. In the two previous models on economic growth, we learnt about the Harrod-Domar and the Solo growth models. Both these models, and especially the Solo model, acknowledge the importance of technology as a determinant of long run economic growth, but neither had an explanation about the drivers of technological progress. In the Harrod-Domar model, the effect of technological change on growth was captured indirectly via the capital output ratio that was assumed to be constant. Technological change would raise the long run growth rate by lowering the capital output ratio for any given savings rate in this model. However, the main insights from this model focus not on technology, but on the importance of savings for long run growth of output. An increase in the rate of savings would lead to a proportionate increase in the long run rate of growth output in this model. The Solo model introduced an aggregate production function with diminishing factor returns and constant returns to scale. Unlike in the Harrod-Domar model, the capital output ratio was a variable determined within the Solo model. It highlighted the role of technological progress primarily in two ways. First, in the Solo model, without technical progress, there was no growth of per capita income in the long run steady state. Second, once the role of technical progress was incorporated, the long run steady state rate of growth of per capita income was determined solely by the rate of technological progress. In sharp contrast to the Harrod-Domar result, an increase in the saving rate led to an increase in per capita income levels in the steady state, but it did not influence the long run rate of growth in the Solo model. The Solo model stressed on the limits to growth from factor accumulation owing to diminishing returns to capital and emphasized the importance of technological progress for long run growth. However, it offered no explanation for the determinants of technical change. The model had no inbuilt mechanism explaining why certain countries experienced a faster rate of technical progress than others. Rather, technical or technological progress was viewed as an exogenous factor appearing much like manna from heaven. The literature on endogenous growth, also known as the New Growth Theory that appeared in the 1980s, addressed precisely this lacuna in the literature on economic growth and added insights on the possible factors determining the pace of technological progress. This literature emphasized that the process of technological progress and innovation occurred simultaneously as a country undertook savings, investment and capital accumulation. In this sense, the determinants of technological change were actually endogenous in the process of capital accumulation. It also took a broader view of capital formation and emphasized that it included both physical as well as human capital formation. As we shall see below, the endogenous growth models emphasize the role of saving and also the role of government in influencing the long run rate of growth in an economy. This contrasts with the result flowing from the Solo model that essentially focused on the supply side, that is on the production of output, ignoring the role of demand and had little role for the government. Consumption in steady state and golden rule. In the previous model, we had discussed the role of savings in the neoclassical growth model. In the solo model, a higher savings rate did not affect the long run growth rate, but led to a higher level of capital per capita and income per capita at steady state. However, an increase in savings comes at the expense of lower consumption, which implies lower welfare and standard of living. Note that if the savings rate is too low, per capita income would also be low, and so would consumption per head. For example, in the limit, if the saving rate is 0, there is no capital accumulation, and hence output and consumption is almost 0. However, when the savings rate is high, capital stock would be very high, as would be depreciation, and hence a large amount of investment would be required just to maintain existing levels of the capital stock in steady state. This would drive consumption to very low levels. For example, if the savings rate is 1, people will save all their income, so capital and output would be very high, but consumption would be 0. So logically, there must exist a saving rate S star between 0 and 1, that is S star lies between 0 and 1, where per capita consumption in steady state is maximized. It is called the golden rule saving ratio. For S star greater than S, consumption would be increasing, whereas for S greater than S star, consumption would be decreasing. The level of capital associated with the optimal saving rate S star that yields the highest level of consumption in steady state is known as golden rule capital stock. We can write C is equal to y minus Sy, which is equal to 1 minus S function of K, which is a function of savings, where C is the steady state per capita consumption, S is the saving rate, K is capital per capita, and Y is a function of K is the per capita production function, which is increasing in K as discussed in the previous module. Note that the steady state K is an increasing function of S. As S changes, say increases from a low value, there are two opposing pulls on C. 1 minus S falls, but F, K, S rises. At the golden rule value of S, the opposite forces are balanced and the product, which is C, is maximized. Endogenous growth models. Factors affecting technological change. The neoclassical growth theory of Solow assumed that the rate of technological progress was determined by exogenous factors outside the model, and that these factors were independent of economic activities. Neoclassical theory thus implied that long-run growth rate was given exogenously, that is, from outside the economic system. Endogenous growth theory, on the other hand, proposed that the rate of technological progress and hence the long run rate of economic growth can be influenced by economic factors. In particular, technological progress takes place through innovations in the form of new products, processes and markets, many of which are the result of economic activities. A higher pace of economic activity can in turn raise the pace of innovation process by giving firms more exposure and more production experience. Most of the innovations are the result of research and development expenditures and various economic policies with respect to international trade, competition, education, taxes and intellectual property can further affect the rate of innovation by influencing private costs and benefits of doing R&D. The assumption of diminishing marginal product of physical capital in the Solow model entailed that as more and more of capital was accumulated, its productivity or per unit contribution to output declined. An important contribution of the endogenous growth theory was that it explicitly recognized that the capital endowment of an economy comprised both physical and human capital. This led to the central insight from these models that as the economy's stock of human capital improved, it mitigated the decline in marginal product of physical capital. Therefore, as capital accumulation occurred, diminishing marginal returns to capital was not inevitable. Rather, there might be a constant or even increasing marginal returns to capital. That is, the slope of the aggregate production function need not diminish with an increase in per capita capital stock. Rather, the slope might remain constant throughout or even increase. This may be further explained as follows. Human capital essentially refers to an educated or skilled labor force. An economy that invests in human capital by setting up schools, universities, research centers, laboratories, etc., essentially creates an environment conducive for learning, innovation and technological progress. As a result of more training and learning programs, human capital becomes more efficient and productive. Moreover, as workers acquire skills and gain experience with machines, there is learning by doing. So they innovate, learn newer techniques, gain more knowledge and their productivity improves. Moreover, human capital formation can go hand in hand with physical capital accumulation. For example, as new production facilities are constructed and new machines are produced and put into use, the gains from these investments can be then reinvested and used in building more schools, healthcare facilities, training and research and development facilities. Since physical capital accumulation itself can lead to technological progress, hence diminishing marginal product of capital need not set in. The government can also play a role in improving the pace of capital formation and technological progress via subsidies for education, research and development. It can also strengthen institutional mechanisms such as patent laws, etc., that creates incentive for innovation and creation of new technology. The AK model, the assumption of constant returns to capital. We now introduce a simple version of an endogenous growth model where it is assumed that the aggregate output is proportional to capital and there is absence of diminishing returns to capital. The model displays both constant returns to scale and constant returns to capital and referred to as the AK model. An early version of AK theory was produced by Frankel in 1962, who argued that aggregate production function can exhibit a constant or increasing marginal product of capital. This model deviates from the standard assumption of neoclassical growth theory. It emphasizes the role of investment in physical capital, which further enhances the development of human capital. As firms accumulate more and more of capital, some of the increased capital will be intellectual capital that enhances technological progress. This technological progress prevents any reduction in the marginal product of capital. The state of technology is introduced as a variable in the production function and it is represented by capital A. This technological parameter essentially tells us how much output can be produced using a given quantity of capital and labor. Therefore, the production function for this model is defined as y is equal to AK, which is function 1, where A is a constant that reflects the level of technology and K is aggregate capital, both human and physical capital. This model assumes that the production function is linear in the only input capital. Thus, K can be assumed to include not just physical and human capital, but the stock of knowledge and even the financial capital in the economy. The above production function reflects both constant returns to scale and constant marginal returns to capital. Constant returns to scale implies that for a given technology, if we increase capital by some proportion, say m, then output also increases by the same proportion. That is, A in brackets mk is equal to my. Further, constant marginal returns to capital implies that when capital increases by 1 unit, the amount by which output increases is a constant given by A. This implies for the above production function 1, we have mpk is equal to dy by dk, which is equal to A. Constant marginal productivity of capital may be observed when technological progress occurs alongside accumulation of physical and human capital. Human and physical capital interact with each other to enhance the efficiency of resources. The greater the stock of human capital in a country, the higher would be the marginal product of physical capital. The more skilled the workforce, higher would be the productivity of machines. Also, the greater the stock of physical capital in an economy, the higher would be the marginal product of human capital. The more machines there are in an economy, the greater would be the returns from investing in skills and education. Economic growth in the AK model. We can show that the rate of growth depends upon the rate of savings and investment in an endogenous growth framework. We assume that the economy is closed and that population is given and there is no population growth. So, the rate of growth of per capita output is determined entirely by the rate of growth of output. Given the production function, the rate of growth of output in turn is determined by the rate of growth of capital. Since the production function is given by yt is equal to AKT, which is 1, so yt plus 1 minus yt divided by yt is equal to A in brackets kt plus 1 minus kt, this all over AKT, or gy is equal to bracket open yt plus 1 minus yt divided by yt, which is equal to bracket open kt t plus 1 minus kt bracket closed divided by kt, which is equation 2. It is assumed that the saving rate is constant, that is a constant fraction of the income S is saved. So, the total aggregate saving ST is equal to SYT, which is equation 3. Also, in a simple closed economy without government, the equilibrium condition is given by equality of investment and aggregate savings, that is IT is equal to ST, which is equal to SYT, which is equation 4. In each period, a fraction delta of the total capital stock depreciates. So, the total amount of depreciated capital at each time period is given by delta KT. In this model, the process of capital accumulation may be denoted as follows: Kt plus 1 minus Kt is equal to It minus delta Kt, which is equation 5. There is capital accumulation or addition to the total capital stock. That is, the left hand side of 5 is positive as long as new investment IT exceeds depreciated capital stock delta KT. We can also write 5 as follows: Kt plus 1 minus Kt is equal to Syt minus delta Kt using equation 4 above, or Kt plus 1 minus Kt is equal to Sakt minus delta Kt using 1 above. Now, dividing both sides by Kt, we get Kt plus 1 minus Kt divided by Kt, which is equal to Sa minus delta, which is equation 6. So, Gy is equal to Kt plus 1 minus Kt divided by Kt, which is equal to Sa minus delta. From this, it can be seen that in an endogenous growth framework, the growth rate of the economy depends positively on the savings rate S. This is in contrast to the neoclassical model, where the long run rate of growth of per capita output was independent of S. In fact, this simple model demonstrates that even without any exogenous technical progress, the technological parameter A is constant. Aggregate output can keep growing indefinitely as long as SA is greater than delta. This results in a sharp contrast to that in the Solow model, which showed without technical progress, there was no growth in per capita output in the long run equilibrium. In the Solow model, rather than faster capital accumulation, it was the pace of technological progress that determines a country's long run rates of growth. In the AK model, higher savings leads to higher growth by leading to higher investment and physical capital accumulation. As explained above, accumulation of physical capital further enhances human capital formation, which further raises the productivity of physical capital so that there is no tendency for diminishing marginal returns to capital. Skill formation as a foundation of growth. Another approach to human capital, which has been introduced by Robert Lucas, uses the production function y is equal to k raised to the power of alpha HL raised to the power of 1 minus alpha, where H is human capital per person. It is assumed that human capital evolves to delta H divided by H, which is equal to 1 minus mu, where mu is time spent working and 1 minus mu is time spent acquiring skill. The variable H is exactly similar to labor augmenting technical progress in the Solow model. The new element is that the growth of this factor depends upon 1 minus mu. Any policy that leads to a permanent increase in time people spend to obtain skills generates a permanent increase in the growth of output per worker. Implication of endogenous growth models. The endogenous models have several interesting implications. First of all, as explained above, they emphasize the importance of saving and physical capital accumulation for long run growth in the economy. This is in contrast with one of the central results in the Solow model, where long-run growth was independent of the saving rate. Second, these models underscore the link between physical and human capital formation. In doing so, they bring out the critical contribution of human capital in fostering technological progress that can prevent the setting in of diminishing marginal returns to capital. The Solow model had no explanation for the determinants of the pace of technological progress and did not differentiate between physical and human capital. In contrast, in the endogenous growth framework, growth of productivity is not accidental or exogenous, rather it is brought about by greater savings and investment in physical and human capital. Third, these models also highlight the important role of governments in influencing the process of growth. Government policy can play a crucial role by fostering growth of human capital and creating an institutional framework, that is patent regime, that is conducive to innovation and generic research. This creates a case for specific policies, for example, public funding of education and knowledge creation. For example, funding public schools, colleges, university and fundamental research initiatives. Policies promoting savings, policies of openness to international trade and investment flows that can enhance domestic productivity and motivation by providing access to cutting-edge imported technology, etc. Finally, an important implication of the Solow model is the notion of convergence. This concept of unconditional and conditional convergence were discussed in detail in the previous module. However, convergence in growth rate is not inevitable in the endogenous growth framework. In practice, much of the observed cross-country variation in growth rates is attributable to differences in productivity growth. This suggests differences with respect to human capital formation, capital accumulation and role of government may hold the key to understanding differences in productivity growth as per the implication of the endogenous growth models. Conclusion. In this module, we saw that endogenous growth models try to provide explanation for the factors that affect technological progress. It is shown that these factors are inherent in the very process of factor accumulation. Endogenous growth theory also suggests that if government policies can boost investment, it not only increases the steady state capital stock, but permanently affects the growth rate. Theories of endogenous growth have been criticized on the grounds that they are inappropriate for developing economies where economic growth is mostly impeded by inefficiencies arising from poor infrastructure, inadequate institutional structures, imperfect capital and goods market. However, the endogenous growth framework does not incorporate structural rigidities and as a consequence, its applicability to cross-country development comparison is limited. Further, it has also been argued that the model fails to allow for adequate transitional dynamics with the growth rate changing instantaneously with changes in parameter values. Summary. The main insights from our discussion in this model can be summarized as follows. First, the golden rule capital stock refers to the level of capital stock associated with the optimal golden rule savings rate for which per capita consumption is maximized in the Solow steady state. Second, the neoclassical Solow growth model emphasized the importance of technology for long run growth but has no explanation for what drives technological change. Third, endogenous growth model emphasized that human capital formation that accompanies physical capital accumulation is an important driver of technological progress. Fourth, unlike the Solow model, endogenous growth models are based on the assumption of constant or increasing marginal returns to capital. Fifth, endogenous growth models highlight the importance of savings and capital, both human and physical accumulation for economic growth.